On Monday, we talked about gravitational fields in the context of the bigger context of fields in general. A field is a region that is kind of an invented concept, but it's a region in which a force can be experienced by an object. And specifically for gravity, a gravitational field, it's a region in which a gravitational force can be experienced by something with mass, by matter. The reason we invent the idea of gravitational fields is because we have to have some way of describing gravity when there's nothing to experience it. We know about a force, right? A force is defined as a push or a pull. When I have an object in the Earth's gravitational field, it will be pushed or pulled. When I put the board marker here, right here, 2 meters above the Earth, it's pulled towards the Earth. There's a force of gravity acting on the board marker, which ultimately comes from that curvature of space-time that we talked about, right, of the Earth. In the end, there's a force of gravity. If I take that board marker away, though, the curvature of space-time doesn't disappear. Gravity is still there. See, that cone that is caused by the Earth, the denting of the fabric of space-time, hasn't changed at all. So we have to have a way of describing that. Our way of describing that is fields. A force requires something to cause the force. It also requires something to experience it. But a field simply requires the producer. If you've got force, if this is our curvature of space-time, you need something to cause it and something to experience it. In order to have a field, all you need is this, something to cause it. All right, a gravitational field is a vector field. We say it's a vector field because it has a direction associated with it. If I was to put an object in that field and expect it to move towards the other object by gravity, okay, because of the gravitational field, then the gravitational field must point or must act in a certain direction. If it does, it's a vector field. There are other fields that we talk about in Physics 30 that are also vector fields, an electric field, a magnetic field. But there's also scalar fields. Say heat. Heat. Okay, over here in the wintertime, Tori feels it a little bit more than other people probably. This is, for whatever reason, they put the heat along the top of the ceiling there. Heat rises. I'm not sure why it wouldn't go close to the floor, so that it could heat the room a little bit more efficiently, but they put it up here, okay? In the end, there's heat that comes out of this little thing that goes all the way across the room here. Heat can be considered to be a field because there's influence. It's a region in which it can act on something. Loosely, we could call it a field, but it doesn't influence us in a particular direction. It just influences us. So we're going to say that a heat field would be a scalar field. A light field would be a scalar field. A gravitational field would be a vector field because it influences other masses in a particular direction. Well, today we're going to describe gravitational fields with equations, two equations, one of which is a rearranged form of something we've already done. The other one is brand new. The first one, we're going to say gravitational field strength. Notice the absolute value signs around it again, just like the force of friction, just like centripetal force, centripetal acceleration, gravitational force, gm1 m2 over r squared. Gravitational field, it's a vector field, but we're not going to learn the direction of the field by using the equation. It's equal to g times m over r squared. This is the field surrounding a producer. We call it the producer equation. If we have information about what causes the field, we can use this equation. G is 6.67 times 10 to the minus 11. R is the distance that's from the center of the producer. So if you're trying to find the gravitational field strength 10,000 kilometers from the center of the Earth, then it would be 10,000 kilometers, except we convert it to meters. And M, be careful on this one. M is the mass of the producer. in kilograms. If I've got the board marker in the Earth's gravitational field, I've got two masses, the mass of the Earth and the mass of the board marker. If I'm going to use the producer equation, then I'm going to use the mass of the Earth because the Earth is the producer. In that case, I wouldn't use the mass of the board marker. G, by the way, is the gravitational field strength, of course. And the units for gravitational field strength, we could say are newtons per kilogram, or we could say, you know what, I'll tell you the other one in a moment here. I want to leave that as a little cliffhanger for you. The other equation, and this is the one that you might recognize, the gravitational field strength is equal to the gravitational force divided by the mass. That's just a rearranged form of F is equal to m times g. Except that in all the other cases, we've assumed g is 9.81. Now we're actually finding the value of g given the mass of the experiencer, not the mass of the producer. Use the mass of what's experiencing the gravitational field because this is the experiencer equation. And F would be the force of gravity felt by the experiencer. Or you could say it's the weight. Because in the end, the force of gravity felt by the experiencer is the weight of the experiencer. G, of course, again, is the gravitational field strength. We said that that's the same thing as saying F is equal to m times g, g being 9.81 meters per second squared. G, gravitational field strength, g, acceleration due to gravity, can be measured in newtons per kilogram, or it can be measured in meters per second squared. It's the same thing as the 9.81, except it might be a different number depending upon the circumstances. It's an acceleration due to gravity, except that now we're calling it gravitational field. So really, we've used gravitational field lots this year, 9.81 meters per second squared. Now we're saying, look, we're going to call it something different. Instead of calling it acceleration due to gravity, we're going to call it the gravitational field strength. It amounts to exactly the same thing. But now we have a way of actually finding its value. We don't have to assume that it's 9.81 meters per second squared. Bless you. If you're on the surface of the Earth, it'll still be okay to assume 9.81. If you're somewhere else, then you should calculate the gravitational field strength. So here's the rule of thumb. If you have information about what causes the field, then you should use the first equation. If you have information about whatever it is that experiences the field, then you should use the second equation. If you have information about both what produces the field and what experiences the field, you can use whichever one you want because you should get the same answer. In the end, the gravitational field produced by the Earth, a total distance of 1 meter above the Earth, is the same field as the gravitational field experienced by this board marker when it's 1 meter above the Earth. So the producer equation and the experiencer equation should give you the same value if it's the same situation. Just depends upon what you have more information about or which one you choose to use, which one fits better. All right? Got some masses here and some radiuses here. Table on page, I'm not sure what page it's on, chapter 4. You may need to refer back to that table as you're working on some problems. Okay, clearly you don't need to memorize into those numbers any more than I do. You need them on a test or quiz, you'll be given those numbers. But for homework, you might want to refer back to table 4.1, beginning of chapter 4. All right, question 4.5 on page 218 says, calculate the magnitude of the gravitational acceleration on an object, the equator of the surface of the Earth and the Moon. A couple of things here. First of all, gravitational acceleration, gravitational field, same thing. So we're looking for what we just found. Even though we called it gravitational field a minute ago, now they're calling it gravitational acceleration. Doesn't matter. Second of all, I don't know about you, but man, does this person look huge or what? Like this person is the diameter of the Earth. That's how tall this person is, and about twice the diameter of the moon. We want to find the field strength at the equator of the Earth and the equator of the moon. What do we know more about? Let's do the Earth first, okay? What do we know more about? What causes the field or what experiences the field? Actually, let me ask you another question first. What is it that causes the field, and what is it, bless you, that experiences the field? Got it? Yeah, the Earth causes the field, or the moon in the second case causes the field. What experiences the field? The person. All right, what do we know more about? The Earth or the person? We know that this person is really, really tall, but that seems to be all we know about that person. I think we know more about the Earth. And the Earth is the producer, so let's use the producer equation, right? G is equal to big G M over R squared. (6.67 times 10 to the minus 11 times the mass of the Earth, which you can look on that table, you find that it's, what is the mass of the Earth? 5.98, I think, 5.97 times 10 to the 24 kilograms. And the radius of the Earth, 6.38 times 10 to the 6 meters. What do you predict we're going to get here for the gravitational field strength caused by the Earth on the surface at the equator? Nick, what are you going to predict we're going to get here? 9.81? Probably close, pretty close to that, probably. Let's figure it out then. We're going to say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by bracket 6.38 times 10 to the 6 bracket squared. 9.78. You could say meters per second squared, or you could say newtons per kilogram. Both of those work. So Nick predicted 9.81. We know why he predicted 9.81, right? Because we're talking about gravitational field on the surface of the Earth. But we know that it does vary a little bit depending upon where you are. If we get a value that's 9.78, how confident are we that we're right? Pretty confident, right? Because it's pretty close to that value that Nick predicted of 9.81. If you get a value that's 3.7, you're probably wrong. Okay, somewhere close to 9.81, you're probably right. Something else, you're probably wrong. Yep. Yep. What about on the moon here? Gravitational field strength on the moon. We're going to do the same thing. The moon is a producer as well. We know more about the moon than we do the person. The mass of the moon is 7.35 times 10 to the 22. And the radius of the moon is 1.74 times 10 to the 6. And we got to square that. So let's do that one. 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22 divided by bracket 1.74 times 10 to the 6 bracket squared. 1.62 meters per second squared, or newtons per kilogram. We want to find a ratio. Do you guys remember what we do when we want to find a ratio? You want to compare two things or find a ratio? What's the one word that means the same thing as compare or ratio? It's a D word. Divide, right, divide. Remember we said we wanted to compare my age to your age? We divided my age by your age. Compare the Earth's gravitational field to the moon's gravitational field. We're going to say 9.78 divided by 1.62. And when we do that, we end up getting 6.04. So the ratio would be 6.04 to 1. All right, since we're masters of this example, let's take a look at the questions that go along with that on page, what happened there? Page 218, there we go. Just have a quick look at question number 1. I just want to point something out. Question number 1 says a satellite orbits Earth at a distance of 3 times the radius of the Earth, 3 RE. What does that mean? Well, if this is the radius of the Earth, then the satellite is up here 3 times the radius of the Earth up here. So the total distance from the satellite to the center of the Earth would be what? 4 times whatever the radius of the Earth is. So all you do is say 4 times 6.38 times 10 to the 6th, the number that's given to you on your table. All right, let's have a look at question number 2. It says an 80-kilogram astronaut is in orbit 3.20 times 10 to the 4 kilometers above or from the Earth's center. Using the data from the table that we copied over onto this page, what's the magnitude of the gravitational field strength at the location of the astronaut? Now, you see this question, like, look at what you got, okay? Look at what we've got here. We've got an astronaut, we've got the Earth. One of these things is the producer that causes the field, and one of them is the experiencer that feels the field. Which one is which? Forget about what I know something about right now, what I have data about. Which one is the producer? Which one is the experiencer? The astronaut. Tell me which one the astronaut is. Taylor, is the astronaut the producer or the experiencer? Yeah, the astronaut feels the field, experiences the field, right? What about the Earth? Well, the Earth must therefore be what, Julia? Good. The Earth is going to be the producer, the thing that causes the field. Now, we know something about both, right? We know something about the experiencer. His or her mass is 80 kilograms. We also know something about the producer, which is the Earth, and the mass of the Earth and the radius of the Earth given to you on this table. What do we know more about? The producer or the experiencer? The Earth or the astronaut? You know what? We know more about, I think we know more about the producer. We know more about the Earth. We know its mass and we know the distance from the Earth that the astronaut is. Okay, that's all information about the producer. But let's say you didn't notice that. Okay, let's say you wanted to use the experiencer equation. That's a perfectly valid equation to find the gravitational field strength at the location of the astronaut. Let's use the mass of the astronaut if I'm using the experiencer equation. And, oh wait, what's the force of gravity felt by the experiencer, by the astronaut? We don't know. I tried using the experiencer equation. What did I find? I found that I didn't get the wrong answer. I just found that I had too many unknowns, so it wasn't going to work for me. That's okay. Try that first. Go ahead. It's okay. Just make sure you don't use the mass of the Earth there. Okay, use the mass of the experiencer. All right, if that doesn't work, let's go to the mass of the producer equation. Gm over r squared. G is 6.67 times 10 to the minus 11. M is the mass of the producer, which in this case is the mass of the Earth. That's on the sheet above. And r is the distance from the center of the producer, which is 3.20 times 10 to the 7 meters. Why did I say 10 to the 7? It's just 10 to the 4 up there. Where does that 10 to the 7 come from? Yep. We got to convert it to meters, and we do that by multiplying by 1,000, which is 10 to the 3. So it becomes 10 to the 7. Let's square that. All right. Look, we got everything we need here now, right? So the producer equation, the experiencer equation, both valid. Which one works better? The producer equation works better. We do the math on that one, and it works out to be 3.89 times 10 to the minus 1. And we could say that that's meters per second squared, or we could say now, this new set of units that we have, newtons per kilogram. In question B, we're doing almost the same thing, except we're using data for the moon now. G is equal to gm over r squared. 6.67 times 10 to the minus 11 times the mass of the moon, which I think is 7.35. Yeah, 7.35 times 10 to the 22. Divided by the distance, same separation distance, 3.20 times 10 to the 7. Square that, do that math, it should work out to be 4.79 times 10 to the minus 3. Newtons per kilogram or meters per second squared. If you wanted to find a ratio between the two, you'd divide them, of course. All right, let's take a look at question number 3. It says the highest satellites orbit Earth at a distance of about 6.6 times the radius of the Earth. That's a long ways away, right? The radius of the Earth is 6.38 times 10 to the 6 meters. 6.6 times that is a big number. We want to find the gravitational force on a 70-kilogram astronaut at this location. All right. We got a producer and we have an experiencer there. Here, right? We have the Earth and we have an astronaut. Which one's the producer, the Earth or the astronaut? William, producer, Earth or astronaut? The Earth, good. The experiencer, therefore, is going to be the astronaut, right? What do we know more about, the Earth or the astronaut, the producer or the experiencer? I don't know. It looks like we know quite a bit about both, right? Pick an equation. I'm going to go with the Earth. Actually, you know what? I'm going to go with the experiencer equation. And the reason I'm going to do that is because I'm looking for force, right? I'm looking for the force felt by the astronaut, felt by the experiencer. Let's rearrange that. And lo and behold, look, we get this equation that we've used a million times before, but we can't assume that G is 9.81. That's the only thing. M, the mass of the astronaut, 70 kilograms. Oh, but look, we don't have G. So let's find that using information about the producer, using the producer equation. Now you got to make sure you use the mass of the Earth, the mass of the producer. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by the radius. Oh, the distance is, 6.6 times 6.38 times 10 to the 6 squared. Because, of course, we're talking about 6.6 times the radius of the Earth from the center. All right, let's figure out what that number is. We get 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Remember, we're using the mass of the producer here. Divide it by, use some brackets definitely here, 6.6 times 6.38 times 10 to the 6, and the brackets square that whole number on the bottom. You get 0.22457, 0.22458. Newtons per kilogram or meters per second squared. If that's the field strength that's caused by the Earth at that point, then that's going to be the field strength experienced by the astronaut at that point. So let's plug that in here. And when I do that, I think I should end up getting the 16 newtons. 16 newtons that's given to us there as the answer. Let's try this one, page 220, 4.6. What's the mass of a 60-kilogram student on Mars and on Earth? And what is the student's weight at the equator on the surface of Mars and the Earth using data from table 4.1 again? I'll tell you what, question A, easiest question in the world. And by the way, you're going to get one of these either on your unit test coming up on Tuesday or your final exam. I can't remember which one it appears on. What is the mass of a 60-kilogram student on Mars and the Earth? What's the answer? 60 kilograms. If I said, what's the weight, then it's the force of gravity, right? But the mass is the mass, it's 60 kilograms. Sometimes the easiest questions in the world become the hardest questions in the world because we look at it like, I don't know, can't possibly be that easy. Okay, you got to be more to it than that. Well, sometimes there isn't. All right, we want to find the student's weight at the equator of the surface of Mars and the Earth. weight is force of gravity. And we'd probably use the experiencer equation to find the force of gravity, just like we did in the last question. So we'd say 60 kilograms, that's the experiencer's mass, times, we don't know what G is though. We certainly can't assume that it's 9.81 meters per second squared. Let's find the field strength on Earth using the producer equation. I think we found that earlier in another question, didn't we? Field strength caused by the Earth at the equator was 9.78. Okay, we can do the same thing for the field strength caused by Mars. Multiply that by the mass of Mars. 6.42 times 10 to the 23. Divide it by r squared for Mars. 3.4 times 10 to the 6. Let's figure out what that one is. $3.877. So all I'm going to do here now is multiply this by 9.78, and then I'm going to do the same thing for Mars, multiplying it by 3.88. Did anybody see something else I could have done besides what I just did? Yeah, I used the producer equation and I used the experiencer equation. And it worked, right? Does anybody see something else I could have done here? No? Let me show you this, and then I'll flip this page back so you can finish copying that if you haven't already, all right? Here's the producer equation. This would be the mass of the producer, right? Here's the experiencer equation. This would be the mass of the experiencer. If an astronaut is at a certain spot in space, and that astronaut experiences a field that's caused by something else, then those two fields, the producer equation and the experiencer equation, can be set equal to each other. So in other words, G times the mass of the producer over R squared is equal to F over the mass of the experiencer. Let's rearrange that. When I do, I get F is equal to G times the mass of the producer times the mass of the experiencer over R squared. In other words, when I set the fields equal to each other, the producer equation and the experiencer equation, I get Newton's law of universal gravitation, Gm1m2 over R squared. I could have done that back here. Instead of finding the field strength and then using the producer equation, then using the experiencer equation to get F, I could have just went straight to F is equal to Gm1m2 over R squared and got my answer there. Make sense? Either one of those methods would be good, okay? You either need the field strength caused by the producer and then plug it into the experiencer equation, or you need to use Newton's law of universal gravitation. Either is fine. All right, let's try those three questions, please, on page 220.